In software engineering, we are taking chapter number 23, which is testing conventional applications. Software testing fundamentals. So whenever we test a software, what is the main goal, objective of testing? The first thing is to find errors, and the second thing is with minimum of effort. So finding errors in minimum effort, that is the time and effort should be less. For that, the software has to be testable. It can be your software, web app, mobile app, embedded software, real-time software. They need to be testable. The way we can test it should favor James Back. He defines what is testability. That is the easiness to do the test. So he says software testability is simply how easily a computer program, a software can be tested. That means, in other words, a tester find it easier to test a program. So what are the different characteristics of a software when we say it is testable? All the software should have certain characteristics that will make that software or the system testable. The first thing is operability. This operability is the better the software is working, the more efficient or the more efficiently we can test it. Because when we are designing the software, when we are modeling the software, when we are making different the software development life cycle phases, and we implemented the quality, that is, we always kept in our mind the quality. That means there will be few bugs, few errors, and these errors, they will not block the execution of test. So most of the test, first of all, the test will be less, the test cases will be less, and the result will be finer. The second is observability. What you see is what you test. Because test main problem is finding the error, locating the error, and fixing the error. So if you are able to see everything, that is the input what we give, it can give distinct outputs. So the state of your software, the variables, if they are visible, you can query them under execution. Even if the incorrect output is coming, you are able to identify it. You can analyze it. You can find out what error may be. And the internal errors, which are so difficult to find, if they can be automatically detected and reported, that means your software has testability and especially observability. Controllability. If you are able to control your car's speed, then there is unlikely chances that you will meet any accident. Most of the accident happen when you have high speed. So here comes the same thing. If you are able to control your software, then the testing can be easily optimized and automated. Most of the time semi-automated. So if the software is under your control, that is, all the possible outputs can be generated through certain combination of input. The input output, the formats are consistent everywhere and they are properly structured. So the software and hardware states and the variables, they can be controlled directly by the person who is testing, that is the test engineer. This is the controllability. So test can be easily, conveniently specified, automated and reproduced because the software is under your control. So it can be tested with control. Very important aspect of your testability. Okay. Now the next thing comes is decomposability. When you can decompose, for example, you have some word. If you are able to divide it into some parts, you will be able to do them more easily, efficiently. So by controlling the scope of testing, we can quickly isolate the problems and we can perform the testing and retesting. See, the software system is built from different classes, independent modules, and when we are able to test them independently easily, then we can do the integration and the system etc. testing. Simplicity. The less there is to test, the more quickly we can test it. What does it mean? If the software is simple, the test cases are simple, they are less test cases. So the simplicity is all about KISS, keep it simple. If you are making even a complex software or a large software, if you are able to make it simple, for example, the functional simplicity, that is, the feature set should be minimum, which are bare minimum to meet the requirement. Putting everything which are redundant or not required is not advisable. Structural simplicity. If the architectural design is modularized, is compartmentalized, so this modularization will help in avoiding the propagation of faults. When the coupling is less, when the cohesiveness is higher, the structure is simple, then the fault may not propagate because of the interfacing. Code simplicity. If you have used certain standard to write your code, and this standard is known everywhere because we need to follow certain, say, IEEE or ISO, some standard. For example, aircraft, MISRA standard is there. So a coding standard, if it is adopted, easily we can inspect and maintain the software. Stability. When your software is stable, that is, quality-wise it is good, and the changes are less, because if it is good, there will be few changes. The disruptions for testing will also be less, will be fewer. If the changes, modification to the software are less, seldom, that is infrequent, they can be controlled when they actually occur. The existing test may apply, that is, it will not invalidate the existing test. Stability is important, and that only comes when it is being properly designed and properly coded with quality in mind. And the software, if it recovers well from any kind of failure, hardware, software, even, it is stable. Understandability. The more information we have about the software or the system, the smarter we will be testing. For example, if you are doing white box testing and if you know about what is going inside, then if some testing comes up with an error, you are able to solve it easily, quickly locate and fix. So the architectural design and the dependencies between all the internal, external and shared components, if they are well understood, then the software is testable. Along with this, the technical documentation, if they are easily accessible, they are well organized, like the design document, the requirement specification, the models, the UML diagrams, they are specific and detailed and accurate. So this technical documentation also helps in a good way to test the software. While designing the test cases, what is a good test case? How will you define that this is a good test case and this is not? So there are, test cases are the beginning of testing. You cannot just go and test. You have to write test cases. That is, what is the use case? What is the precondition? What are you going to test? What are the precondition? What are the post condition? What are the expected results? What are the actual results? And there are so many other things which we write in the test case template. But we cannot just make test case like this. We have to be very sure that it has to be a good test. So there are certain characteristics, attributes of a good test, or we can define it to be a good test when it has a high probability of finding an error. Always testing is done with an intent to find an error. This is a traditional definition. But if you are testing and if you don't get an error, that means you have failed. As a tester, you have failed. So tester must understand the software and how it might fail. So now you have the high possibility and probability of finding an error. That is a good test case. A good test case is not redundant. That means there should not be any duplicacy. For example, if you have written a test case and the other test case, they are eyeing upon the same thing. They are doing the same test, maybe in different way, but the same test. This is redundant. We don't need the test cases to be redundant. Every test case should have a different purpose and sole different purpose to check a different functionality or different, possibility. A good test case should be best of breed. Now the horse coming from Arabs, they are best of breeds in all the horses found everywhere in the world or anywhere in the world. What is the good thing about those horses? They are best of breed. Same thing here. What does it mean when we talk about the testing? See, you will write a test case. You are trying to find out an error. But a test case, if it can find out a whole class of errors everywhere, wherever this error is, that class comes to you. Oh, this kind of error is everywhere. So a good test case is now best of breed. You are not just trying to find out one or two errors, but the whole class, whole breed of errors. That is called a good test case. A good test case or a good test should neither be too simple nor too complex. If it is too simple, it may not be able to uncover the error. Complex, you will not be able to understand it. Internal and external views of testing. Now, even if you are making a hardware or a software, there are always two ways of testing it. Any engineered product, it can be tested in two ways. Let me go to this diagram. Now here, this person doesn't know what is inside the software. He is just giving input and trying to find out the output, whether this output is actually conforming to the expected result. If it is not, there is deviation and there is some error. He will check all the functionality. For example, 10 functionalities are there. He will check for the input. But white box testing or this kind of testing, here the software is open to him. He knows about the software. He knows about all the architecture. He knows about the control path. He knows about the constructs. He knows about everything. And now he is testing. So this engineered product can be tested in two ways. Internal is white box testing. External is black box testing. So what are the two ways? It is not only about software. It can be applied anywhere. In the market, whichever product is there which is being engineered. So here we are talking about two types of testing. The first one is test can be conducted to find out, to demonstrate that each function, whatever functionalities are there, this function is operational. And at the same time, finding out it to be functional. Same time, we are trying to find out the error, search for the error, uncover the error in each of these functions being tested. If the actual output is not meeting the expected ones, then this is the black box testing. External view on this kind of error is reported to the person who is going to debug. This is black box testing. Nothing is known about the internal content we just give the input, we find the output and just verify whether it is correct or not. The second kind of testing is knowing the internal working of a product software system. The tests are conducted to ensure all the internal operations and the components have been adequately exercised. We cannot do the exhaustive testing, but still most of the test cases designed here or made here are trying to find out that all the paths are achieved or traversed at least one time. So black box testing, these tests are conducted at the software interface. We are trying to find out the functionality. That is, this input is there, this is the output. We do not examine or we don't know about or we don't want to know about the internal logical structure of the software. Whether this function is working, it's good. Not, report the error. White box testing. So there can be multiple paths, multiple control constructs. So it examines a logical path through the software and there are different components, they are collaborating. So the collaboration between the components, these are tested by traversing specific set of conditions and the loop test. Because in programming we have different constructs. If, then, else, while, if else, while, do while, switch, there are so many. So if there are 50 ways to go from one place to another, we will test all the 50 cases. White box testing. For a software program, whenever we write our code, it can be C, C++, C#, Python, any of it. There will be a way to put the logic. So it can be loop, if then else, it can be straight line code, it can be looping, it can be a case statement, it can be, as I said, if, while, do while, the switches, so many. So all these are ways to implement your logic, and then we have to test all these paths one by one. That is white box testing, black box testing. They are not testing. They are the philosophy to design a test case. So white box testing, this is also called as a glass box testing, and since we know the internal structuring, we call it as structural testing. So this is a test design philosophy that uses the internal control structure in the component level design in order to derive test cases. This is the component level I am talking about. Every component or a module has different kind of control structure. So this will use this control structure to derive the test cases. So test cases in white box testing are derived such that it is guaranteed that if I am going from New Delhi to Agra, if there are say certain ways, 3 ways, so all the independent paths within a module have been exercised at least once. Then these test cases are derived such that it exercises all the logical decision on their true and false. Because this is how we implement the logic. We use if, the AND operators, the OR operators. Then in software, mostly the problem comes at the boundary, not at the internal values. So we will always check at boundaries. For example, 18 is the age for voting. We'll check at 17, 17.9, 18.1. These are the boundary values check. Then we'll exercise internal data structure to check whether they are valid and the data inside them are kept integral. It can be array, it can be linked list, it can be any kind of data structure we are talking about. So they are checked. These are called the test cases, good test cases for white box testing philosophy. What is the difference between a black box testing and white box testing? What is a black box testing first, and then we'll understand the white box testing. First of all, these two are not testing technique. They are the test case design philosophy. That is, we will create test cases on the basis of black box, and test cases we will design with reference to white box. Now the black box, it is not open to the user, or a user doesn't want to know inside. There are multiple functionality the software is giving, so he will just give you input and try to find out the output for each of the functionality. If the expected input is not matching with the actual input, there is a deviation, and that deviation is reported to debug. If there are 10 functionalities, then we will try to implement all these 10 as test cases. This is black box test cases design philosophy. White box testing, the inside is known, the component level control structure, if it is if else, if it is switch, if it is say other control construct, if then else, we know each of these, and we will try to ensure that all the independent paths, they are traversed, executed at least once. For example, if you are going from A destination to B, there are 3 ways. All these 3 will be a different test case. This is the white box, internal is known. So black box testing, implementation knowledge is not required for who is doing the black box testing. So there is no requirement to know what is inside. In white box testing or test case design, the implementation of the software or the product, the implementation knowledge needs to be known, is required. Okay, all the control structure, the architectural design, everything. In black box testing, it is called as closed box testing also. It is called as data driven testing and functional testing. These are all the same name. Similarly, white box testing, also known as glass box testing, clear box testing, structural testing, or code based testing. White box testing, the same name. Black box testing is generally performed by the end user because he is not aware of what is inside, and there is some independent test group, they can also perform it. But white box testing, because the internal structure has to be known, identifying the structure, creating the test plans, analyzing the source code, this can only be done by the developers. So it is normally done by the software developer or the programmer or the software team. Okay. Now coming to the programming knowledge. You give input and you get the output, trying to see the functionality. So programming knowledge may not be required. White box testing, because you need to know Python construct is different from the C# construct. So the programming knowledge, the coding knowledge should be there, is required. The black box testing examples can be functional testing, the non-functional testing, the regression testing. These are all the examples of black box testing. White box testing, you have path testing, loop testing, condition testing. These are all coming in white box testing. Please remember, if you combine black box with the white box, there is another testing called as the gray box. Most of the time, these two are combined to make a glass box way of test cases design. This is not the testing. These are test cases design philosophy. Basis path testing. In a software, whenever we are going to code, before that, we know how many paths we are going to traverse. So this basis path testing is a white box testing. Actually, it is a test case design technique, and this is proposed by McGraw-Hill. So the basis path method, first of all, if you have written certain procedure or say made a flowchart or made a PDL, that is an algorithm. So the basis path method will derive the logical complexity measure of this procedure, of this procedural design. Using this measure to define a basis set of execution paths, and they are nothing but the test cases. So these test cases which we are going to derive, this derived to exercise the basis set, these are guaranteed to execute every statement at least one. Every path, every route, at least one. Whether it is if then else, loop, case. Flow graph notation. So we also call it as a program graph. And this is all to make or to derive test cases. So this flow graph is depicting the logical control. The control is, in any programming language, you are going to use if, while, do while, until, case, and the simple procedural statements. Instructions. So each structured construct has a corresponding flow graph symbol. That is, every symbol which you see here can be depicted as a graph symbol. So let us consider a procedural design representation. I am showing you a flow chart. Now this flow chart, we know the basis, whenever we started our computer science, we know how to make this flow chart. Now you just have to worry about these diamonds because these are conditional statements. If else, because it can give you multiple paths. So in a flow chart, why not we convert it into more, say, understandable? And this is the flow graph. So we will be converting this flow chart into the corresponding flow graph. Well, we can use the flow chart also, but it is better that flow graph notation can be used, will be used, because you will see what we are going to do here. Every circle which you see here, they are called node, flow graph node, and they represent one or more procedural statements. Okay, I'll show you what is the difference between the flow chart and this graph, because a sequence of process boxes and a decision diamond can map into single node. There are arrows. These arrows are called edge or links, and they represent the flow of control similar to what you see in the flow chart. Every edge, this is very important, every edge has to must terminate at a node. Even if the node does not represent any procedural statement. Statement is simple instruction in the programming language, which you are going to convert. Okay. So let us say if else. So we start from here if, there will be one condition if or the else condition. But I am saying we need to end it. So there has to be a node below. So an edge must terminate at a node. Okay. So we have while, do while, entry controlled, exit controlled. Sequence are some simple instruction, no condition, no compound. Now the area will be bounded by edges and nodes. These are called region. For example, this is a closed region. So all the closed region along with one region which is outside, the outside region. So we will be counting region, number of region which are closed. Along with this, we will be adding one more region which is outside. Now, whatever I just told you, let us convert this flow chart into actual flow graph notation, because actually we are going to compute the complexity, cyclomatic complexity, and then we'll tell you how many test cases we can find out. Okay. So we started with this one. This is the first, yes or no. This is a conditional statement. Now, if this is a conditional statement, there are two paths. This is the first path. So where it is going 11. So we'll make a node 1 and we will terminate it into 11. First thing is done. Now coming to 2. 2 is in square box, so it is not condition, it is not even compound. So it is just an instruction. It can be addition, it can be a printf. We don't need it now. This is the difference between flow graph and this flow chart. We are only concerned about the diamonds. So 2 and 3 will combine. 2 and 3 will combine. And now 3, again, it will take you to yes or no condition, if or else condition. So 3 will take you to 4, 3 will take you to 6. So we have to have a node for 4, a node for 6. Okay. So let us combine this. But what do you see here? 4 and 5 are simple boxes. That is, there is just processing. There is no condition, no if else, no path or construct, logical construct. So 4 and 5 will combine, will make node. Now coming to 6. 6 is taking you, again 6 is a conditional statement. So it is taking you to 7 and 8. So we'll make a node for 6, we'll make a node for 7, we'll make a node for 8. Okay. So we'll make a node. I told you for if what we are going to do. So we have one node starting and ending in 2 node, and those 2 again ending in another node. So this is the final way. Okay. 7 and 8 you know. But you have to terminate it. It is going to go to 9. So you have to make a 9 also. So you have to end that edges also. Now coming to 10, because 9 is going to 10, 5 is also going to 10. So you have to make a 10 node and just join from 4, 5 to 10 and 9 to 10. Now 10 is again going back to going back before 1. Just take 10 and make an edge to 1. So I hope you got the idea how we converted a flow chart to a proper flow graph node. The rounds are known as, the circles are known as nodes. The lines, the arrows are the data flow, or you can say a flow graph. And these are the regions. The first region is this one. This is the closed region. Let me change the color. This is the another region because this is also closed. Let me make another region. One more region we can see. Okay. This is the third region. This is the third region. So 3 region. And this is not region. See, because this is outside. It is open. So all the open region will be counted as 1. It will be counted as 1. Okay. So we have 4 regions. Now sometimes what happens in the conditional statement are if, else, switch, while, do, while, all these are conditional statement. All these are if, while, until, case, these are conditional statement. But sometimes you have a compound statement with these conditional statement, for example, or, and, nor, and this will give you true or false. So a compound condition can be inside your conditional statement. So how do you make it? If you have a flow chart, you can make it. If you have an algorithm that may be written in some program design language, this can also be translated into a flow graph. How to convert it? See, this is if A or B. So a separate node is created for each of the conditions A and B in this statement if A or B. So this is a simple if condition, but inside this we have A or B. And A or B will give you result always true until A and B are false. So we'll start with A. We'll start with A. So if A or B, then procedure X. So A will give you, if A is true, it will give you X. The next line, then procedure X. So we make a node. As I said, a separate node is created for each of the conditions of A and B. Okay. So until both are false, you have to make conditions. So for A, if it is true, then procedure X. You don't have to worry about B. But since OR is with B, so now coming to B, you'll take the condition B now. Now B is true, again you will get an X. But if this is not, both are not true, what do you get? You'll go to Y. This is Y. And now I told you, you have to end it. You have to end it. So you have to combine this Y and X with a node. And since X is also, you cannot leave X also, which is coming with A. So now combine X also with this node, and then you can follow the path. Because there is end if. So each node that contains a condition is called a predicate node, and it is characterized by 2 or more edges originating from it. Any node from which 2 or more or 1 or more, 2 or more edges are coming. Let me change my sentence. 2 or more. It will be a predicate node. Independent program paths. So we made a flow graph from the flow chart. Now independent path is any path, any route that introduces at least one new set of processing statement or condition. In simple sentence, new edge has to be included. That is the independent path. every independent path must include a new set of edge, this arrow. So independent path must move along at least one edge that has not been traversed. For example, let us find out what are the set of independent path for this flow graph. First one is 1. We start with 1 and then we came here 11. This is the easiest path. This is an independent path. What can be the second path? Let me change the color. What can be independent path? Because we are making set of independent paths. So we are going to 1, 2, 3, then 4, 5. Then you can go to 10, then 1, back again, and coming to 11. This is path number 2. This is once again an independent path. Now coming to the third path. 1, go to 2, 3, then 6, then 8, go to 9, 10, 1, and then 11. Now you are able to see that every time we are taking a new edge, every time a new edge is introduced. Let me show you one more path. Okay, I'm taking different color. Okay. So now path number 4. This is one of the set of independent path. We start with 1, go to 2, 3, go to 6, then 7, then 9, then 10, and 1, and then 11. Again, one of the edges included, new edge is included. But there are certain paths which are not independent path. Because if all these path 1 to 4 has been taken, I'll make one more path and you will be saying by yourself that no, this is not a path because it is already including all the paths which we have already covered. So it is not a independent path. Okay, just see here. Because this path, as we start with 1, 2, 3, 4, 5, 10, 1, 1, and then we go to again 2, 3, coming back. This can be a path. 6, 8, 9, 10, 1, and then 11. So this is not. Why? Because this is simply a combination of already specified path 1 to path 4, and does not traverse any new edges. So path 1 through 4, which we have devised here, constitute a basis set for the flow graph. This is the basis set. Set is a combination of number of multiple independent paths. I hope you got the idea. Basis set is not unique. If you and me are making the independent path, your path may be different, my path may be different. So different basis set can be derived from a given procedural design. Cyclomatic complexity. How many paths to look for? Whenever we are trying to find out the independent path from a flow graph, how many paths to look for? The answer is cyclomatic complexity. Cyclomatic complexity is nothing but it will give you the test cases. How many test cases? So every time when we take the independent path, it should include an edge or a control path which has never been touched, which has never been traversed. So it is a software metric, cyclomatic complexity. It is a software metric that, because we are going to get the number, that provides a quantitative measure, again getting a number, of the logical complexity of a program. This flow graph has been made from flowchart or a PDL, and this gives you the cyclomatic complexity. So cyclomatic complexity defines the number of independent paths on the basis set, providing you with the upper bound of the number of tests or test cases that must be conducted to ensure that all statements have been executed at least one. So cyclomatic complexity is all about giving you the number of test cases or the upper bound, how many paths you have to take. So cyclomatic complexity can be computed in 3 ways. You need to understand how to make this flow graph, then only you will be able to understand cyclomatic complexity. So let us see how many regions are there. Regions are all the closed circuit and one which is not closed, means outside. So how many you see here? R1, R2, R3 and one R4. These are the first thing, 4. Now cyclomatic complexity can be computed by E minus n plus 2. E is number of edges, n is number of nodes plus 2. Edges are simply the arrows, nodes are simply the circles. The third way to compute the cyclomatic complexity is just have to find out the predicate node. Predicate nodes are those nodes from where two or more edges are coming out, which are the predicate nodes. Two or more edges are coming out. So you see the first node, two arrows are coming, so this is the predicate node. 2, 3, two are coming, predicate node. 6, predicate node. Actually, these are the diamonds in the flow chart. So P plus 1, 3 plus 1. How many regions are there? 4. E minus n plus 2. This also will compute to 4. So the cyclomatic complexity of this example is 4. I'll just revise it. Cyclomatic complexity is number of flow regions. The 4 regions are there. So this is these number of edges minus nodes plus 2. So 11 edges are there, 9 nodes are there plus 2. This is 4. So now the third one, which is number of predicate nodes plus 1. So if you see these are, I'm just computing again the edges and nodes. So 11 edges, 9 nodes, and then predicate nodes are 3. 3 plus 1 is 4. So this all is giving you 4 value. So this 4 are the number of test cases. The value of this Vg is an upper bound for number of independent paths and number of tests that must be designed and executed to guarantee coverage of all program statements. This is cyclomatic complexity. Okay. Deriving the test cases. So how do we find out number of test cases? How to make test cases? In design, we might write some flow chart, draw some data flow diagrams, write some algorithm, how the program is going to be actually coded. So these all the inputs can be converted into a graph, and that can be converted to graph. Graph can give you, we can evaluate from graph number of test cases. So this is a simple algorithm called average. You add the numbers and divide by the count of the numbers. And how do we actually make a graph? Now you may ask why we are making a graph, why we are not using only this code or the algorithm. You will see that it is easy to find out from this graph the cyclomatic complexity. And this cyclomatic complexity is nothing but the upper bound of number of test cases we need to generate. And what will be the test cases? The only underlying idea is the paths we are taking. All the paths should be executed at least once. So don't go into the detail of this average code. I'm just showing you that because we have to make a control flow graph, we have to make certain nodes and edges. Please note, all the nodes mainly are concerned with the equivalent analogous diamond of the flow chart. Diamond is all about conditional statement. If, else, switch, do, while, for, and case, switch case. Okay. These are round circles called the nodes, and these nodes specifically we give for the conditional statement, and then the say accompanying or simple say lines like addition lines or some printing lines. So this one from I equals 1 till do while, I equals 1 till sum equals 0, these are just declaration or initialization, but we have to worry about do while. So from I equals 1 to do while, we can regard all this as node number 1. As I said, we are just interested mainly in the conditional statement because that will be the branching and we have to test the branch. Now inside this do while, we have two different testings or checking, and then we have an AND operator. So this we have a compound statement. So we will take first one and second one because both the condition will either be true or false. So we'll take the first one as 2 and second one as 3. So now we have got 3 nodes. The first node for do while and others. Second is for this checking before and third is for the checking after the AND operator. Now after 2, 3 is coming, but from 2 and 3 there will be branching because the condition can be yes or no or true or false. Now when it ends, you have to go to the end because 2 and 3 are the simple path, but if it is not taking that path, it will go to 10, and 10 is what? After end do. Now coming to the fourth, you want to write it, you can write it, make a node, you can make it doesn't matter because you can combine this 4 with 3, you can also combine this 4 with 5. So this 4 has no value in this kind of scenario. Now coming to the next if. In this if also we have 2 and before and after and. Now it is up to you if you want to take this if. If you want to take this if also as a node, you can take. We are not taking if as a node, but if you want, you can take it. So your graph and my graph may be different. Now I'm taking just this value greater than equal to minimum and value less than equal to minimum. Now when if is okay, when it fails, whether it is going to go, it is going to go to 8 and if. So we pointed it to 8. Now after 8, there will be 9, that is the do while will end. So we are going to end do. As I said, every edge has to start and end. Now when this is going on, if the conditions are not met, you have to go again back to 2. So from 9 you have to go back to 2. And this will go on because do while go on and on until the condition is false. From 8 you will go to, see, this 8 to 9. From 6, where are we going? If the condition is true or false, we are going to 7 or 8. Okay, either if is true or if is false. So that is, we are going to from 6 to 8 and 7. So this is the way. One more thing is from 10. If 10 is true, we go to 11. If 10 is false, we go to 12 and then we end at 30. This is end if. Now, if you even don't understand a bit, you just have to take the conditional statement and just see and just make the edge from where it starts and where it ends and name those nodes as some numbers. Okay. So the basis part testing method can be applied to a procedural design or a source code or a flow chart or a data flow diagram. Whichever input you have, you just see the conditional statement and the compound statement and name them as the nodes and join them. So this was the average simple algorithm, and this has a compound conditions and loops. So we took it for the example of test case design. So what are the steps? First step we have already done. Using this design or a code as a foundation, we actually made a control flow graph and we use the symbols and construction rules. And the construction rules, you can just, manipulate it, change it, because ultimate our aim is to execute all the paths exactly at least once. Okay. So 10 you can take if in after 4 if we have not taken, you can take it. So wherever it starts, take a node. Wherever it ends, you can have another node. Okay. So this is a kind of graph we made. Now we know how to find out the cyclomatic complexity. Since we have the control flow graph, now we have simple formula to find out the cyclomatic complexity. Cyclomatic complexity is just the number of cases, or you can say the upper bound. So VG, all this we are going to find out cyclomatic complexity. This can be determined without developing a flow graph. Just count the conditional statement in the PDL or the flow chart or the data flow diagram. How many conditional statements are there? Just count it. Just add a 1 to it, and then that will be your number of cases. The only thing this flow graph is helping you is now you can visually see how many paths are possible, whether these are independent paths or not. Otherwise, you don't have to make this control flow graph, just count the conditional statement, add a 1. But since we are following a formal procedure, let us see how we can compute the cyclomatic complexity, which will be actually the number of cases you have to make. How many regions are here? This is the first region, second region, these are the closed region I am talking about. Third region, and this is the fourth region, this is the fifth region, these are all the closed region. One region is outside, which is the open region. So how many regions we have? We have 6 regions. So these are the number of test cases, or this is the cyclomatic complexity. The second way to find out is E minus n plus 2, number of edges minus number of nodes, plus to compute all these and just add 2 to it. 17 minus 13 plus 2 is 6. So again you are getting the same thing, 6. How many predicate nodes are there? Predicate nodes are there, or those nodes from where 2 or more arrows are coming out. 1, 2, 3, 4, 5. Okay. 5 predicate nodes are there. Just add a 1 to it and that will be 6. So this is a check also. You have 3 formula and they will check that okay, we have got 6 as the cyclomatic complexity, and these are the upper bound of number of test cases you have to make. And then we have to determine a basis set of linearly independent path. Why we are making basis set? You said we have computed already the cyclomatic complexity. Because we know the cyclomatic complexity or the number of test cases, what will be the test cases? You have to write those test cases. You have to execute that test cases. So for that you need to know that which nodes or which conditional options you are going to take. And these are nothing but the path, independent path. Independent path is that if you have checked if x is greater than 0, now you will check if x is less than 0. You will not check if x is greater than 0 again and again. If x is greater than 0, what will happen is one path. If x is less than 0, is another path. So this is the cyclomatic complexity. We are going to find out the path because we already know that the cyclomatic complexity is 6. We'll make 6 paths. So see, 1, 2, then we go to 10, then we go to 11 and 13. This can be one path. Always the first path you choose will be unique because you didn't have any other path. Now you make a second path. 1, 2, 10, go to 12 and 13. Now this is again a unique path because if you see here, the first path you have included 11, second path you have included 12. So these are 11 and 12 are different edges you have included, and that is what we want. Independent path means every time you have to have a special unique edge or the condition or the branch or the control structure included. Let us take one more. 1, 2, 3, 10, 11, 13. Now this again is there because we started with 1 and 2 and then went to 10 for first 2 paths. But second one we went up to 3. 1, 2, 3 and then we went to 10, 11, 13. Now we have these multiple paths and these are all unique paths, and all these we have already explained, but these are the paths you can check. Just see that you don't go to or you don't repeat the path again and again. Just independent path, your unique path, unique route, unique branching, and that is the essence of making the test cases. Test cases cannot be redundant. Test cases need to be unique and they need to find out whole class of error. This ellipsis is indicating that any path through the remainder of the control structure, we can accept it. We can have any after 2. We can have any after 2. As we discussed earlier, just compute the predicate node and just add 1. You will know how many test cases are there. You can find out the cyclomatic complexity also. But the whole idea is after finding the cyclomatic complexity, you have to know the paths also because ultimately you are going to write those test cases. Finally, we are ready for the preparing of the test cases that will force execution of each path in the basis set. Again, I am telling you, the tester, when he is going to test all the test cases, he is sure that all the statements in the program have been executed at least once, and any problem in any of the path is the test case result. So if this is not working properly, any of the independent path, there is an error, and that error has to be fixed, that error after the testing. And there are some independent path, there may be certain path where it cannot be tested in a standalone fashion. It requires some other stub or the driver or whichever you say. Some component have to be made, some code has to be written. So for that you can make this path as a part of another path. For example, you have 6, make it at 5, add a 1 to another. Graph matrices. Now, in order to understand the control flow graph, because control flow graph is all about making it from the flow chart, making it from the PDL, program definition language or design language. Then you have made it from, say, algorithm or a data flow diagram. So whichever input was there in your design or while you are modeling the requirement, making it for the coding, before the construction goes, we have all these conditional statement and all the compound statement we included. We converted them into the nodes and the edges, and finally we made a control flow graph. Now, I already told you, you don't have to make this graph if you don't want, because you just have to compute the cyclomatic complexity, and plus that cyclomatic complexity will give you the test cases. But this data structure which you see here is graph matrix. This is assisting the basis path testing. How does it help? Now, we cannot do the exhaustive testing. So the graph which we are making through this control flow graph, we are making a matrix, and this matrix will give you a clear idea, or the user or anybody else. I'll make a matrix from this flow graph. Okay, I'm making a graph matrix which is essentially the same as what you see on right. So how many nodes are there? How many round circles are there? 5. So 5 nodes are there. So for that we'll take 5 rows and 5 columns. These are the rows I'm numbering. Now I'm going to make again 5 columns. So how many nodes are there? You need to make a square matrix, that is the row and column has to be same, and those should correspond to the number of how many nodes we have. So these are node, and the other one you can just name it as connected to the node. So you have given the number to every node. You can give anything. You can give the Roman values. It doesn't matter. But right now in this example, we are taking the node as numbers, and the edges we have used letters. Again, you can take any of these. You can write your name also. We are giving letters. Okay. Why we are giving this? Because we just need to know which edge is connected, which node is connected to which node by which edge. That is the only thing this graph matrix is giving you. So you'll ask, what is the fun? What is the benefit? I'll just tell you. You'll see the benefit. First of all, 1 is connected to 3. So put 1 and 3 interaction is A. 3 is connected to 4. We wrote B to the intersection of row and column. 2 is connected to 4. 3 is connected to 4. We have already done. Now 2 is not connected to 4. 2 is not connected to 5. 4 is connected to 2. So put a C. 5 is connected to 2. See, 2 is not connected to 5. 5 is connected to 2. That is how we'll go about it. 5 arrow 2 will make put intersection from 5 to 2. And then we have 5, 3. Again, we have 4 is connected to 5. So 4 is connected to 5. This is how we are going to write. And then D is also remaining. So 3 is connected to 2. So we put a D. Now this whole graph has been made. So this graph is quite simple to make, but the essence is these are the edges being connected. There is another way generally people make it. They don't want to give the alphabets. They just want to give 1 here. If one node is connected to another node, then they give 1 here. Just replace 1 here. And other points, other cells are given 0 value. Normally we don't write 0 because it will make it quite clumsy and difficult to handle the row and columns. So they just put 1, and we are also going to put 1. We don't put 0. Now all these values A, B, D, C, G, E, F, they can be replaced by a weight. For example, there is a probability that 5 and 3, this edge is going to execute higher. This is the number of times this is going to execute is higher than the other values. So what we will do is we will put at E, for example, take D also. So we have a probability. So I'll put 0.8 here, and for others we can put 0.2 or 0.1. What does it mean is that I will just check 3 and 2 and 5 and 3. I hope you got the idea. I'll give you one more idea. If the processing time during a traversal of link, we are more interested in the processing time, or you are more interested in memory during the traversal of link. When you are checking memory, for example, 3 and 4, it is 3 and 4 is B. So now I will give a higher value to this 3 and 4, the cell which is intersecting 3 and 4, and others I'll leave. So I will just test 3 and 4 more prominently. Others I may leave, or I can check one or two more. The resources also, I can give a weight here and then check that thing. I can leave others because there can be plenty of test cases. Because I'm interested in memory or resources, I will check only that have a higher weight which I have assigned, or my program leader or manager has assigned. I hope you got the idea. That is why the weights are important. This graph is assisting the basis part testing. The numbers which we give will signify whether we have to test it, or we can just test it later, or we can leave it. That is the option. That is the option. Control structure testing. Control structure is about conditions, is about branching, is about yes and no, is about logic, is about yes, no, 0, 1, etc. So the white box testing is improved. The quality of white box testing if we use various variation of control structure testing. So we have different kind of testing like the condition testing. And condition testing, it exercises the logical conditions in a program. For example, if say voting in some country, if age is say greater than 18, voting rights. Now this is the conditional say equation or instruction, and this type of testing is conditional testing. Data flow testing, we are talking about the data. It can be in simple variable, it can be in data structure. So it selects the test path in the location of definitions and uses of variable. For example, this int A. A will be private, public, protected. Where it will be used, it will be global, it will be local. Testing of all these is data flow testing. Coming to the loop testing. Now this loop testing is without any logic. You'll not be able to write a program, especially for the big projects. So loops will be there. It will be different loops. So the validity of loop constructs has to be tested in loop testing. So there are different types of classes of loops. This is simple loop, just the concatenated loop. That means you may have a loop, along with this you have different loop combined. This is the nested loop I am talking about. Inside a loop you have a loop. You can have multiple loop inside, different loops inside. As I just said, concatenated means addition. So one loop is connected with other loop. They can be dependent, they can be independent. Unstructured loop is all the combination permutation of all these previous three. Simple combined with concatenated combined with nested, all these correspond to an unstructured loops. Okay. Now, how to test these simple loops? Because there has to be a way to test all these loops. So just understand simple loop and nested loops first. That I'll give you an example to better understand it. Okay, let me take an example. What it does inside, we are not discussing. We just have a simple loop for, it will run for 10 times. That can be a simple loop. It may be adding values, it can be printing some values or whichever logic you are putting in. Now first you will give a condition so that the loop is skipped entirely. This loop won't work at all. Then you will give only one pass. For example, I less than 1. In place of 10, you can give 1. It will be one pass. So you can fix a variable upper somewhere, and that value can be changed, and then you can have 2 passes, m less than 2 passes. And what you can do is, if the value is large, so this value is I less than some value, is quite large, it can be m, it can be n. Now you can give a value which is somewhat less than n, it not reaches n. So first skip the loop, 1 pass, 2 pass, and then any value which is inside or well below this final value, say 6, 7, 8, like this. Okay, now the final one should be the boundary. Say for example 100 values are there. This loop will run for 100 times. So just check 99, that is n minus 1, and then 101, which is n plus 1, and 100 is n. If 10 is there, you will check for 9, 10 and 11. This is the simple way to test a simple loop, or you can say these are the steps. In order to test for a nested loop, we will just extend the loop of simple loops to the nested loops. And if we do it, the test will be impractical numbers. For example, just say that we have 3 loops, one inside one. I'm just using for, you can use do while, if else also. Now, these are different simple loops. Now, if you take the permutation combination, for example, the first one is running for 100 times, second is 10, third is 50 inside, then that will be an impractical number to test. Now, Bezier suggested that what you can do is, you start with the innermost loop. Give only minimum value to the outermost loop. For example, the upper 2 loop, outward 2 loops should run only for 1 time, and the inner should run for say 50 times. No, the inner loop has to run like, or the tested like what we learned in the simple loop. That is, skip once, 1 value, 2 value, 2 times, and then check the boundary values, n minus 1, n, and n. Now this is done. Now move outward, give the minimum value to the innermost and the outermost, and then do the simple loop testing for the middle one. Okay, simple loop testing for the middle one. Same thing you have to do. Now coming to the uppermost. Now you check the uppermost loop simply like the simple loop, and then the inner should be given the typical or the least value. Concatenated loop can be of 2 types. The loops are independent or the loops are dependent. If they are independent, don't worry, take these 2 loops and check them as simple loops. If they are dependent, then just what we have defined in nested loops, use that way to do it. Unstructured loops. Now unstructured loops can be any, because nested, concatenated, simple, or these are combined. For that you have to see what looping construct is best suited to actually find out the actual result, or some kind of boundary values, some kind of in-between values, or some kind of simple and nested combination you have to use. Black box testing. Now black box testing, the user is not aware of what is inside. He will only check for the functionality. So this is the technique for software testing. This is the technique of test cases design, which examine the functionality. For example, test 10 functionalities are there. He'll test for 10 functionality. That is what these functions are doing, whether they are working perfectly or not. You are not aware of internal structure or coding, as unlike in white box testing it was done. You were using the basis path, you were using the the cyclomatic complexity, and then all the branching, all the paths have to be covered. That is how we design the test cases for the white box. So black box testing is also called as behavioral testing, functional testing, and the main focus is on the functional requirement of the software. How does it work? Whether all these functions are being executed, they are working fine. Please remember, black box testing is complementary to the white box testing because they both uncover different classes of error, different kinds of error. Okay, I'll tell you what kind of error the black box testing will generate. Let me add one more thing. This black box testing is always done after the white box testing. If you combine these two, there will be another testing called as gray box testing. Again telling different kinds of error, classes of error they find. So as I was telling, BB or black box testing, the error can be incorrect or missing functions. For example, you just have 8 functions, 10 are given to you. The interfacing errors, whenever we combine modules, there will be some integration problem, and these integration or interfacing errors we have to finalize, we have to see. Now errors in the data structures or the external database access, because whenever we are sending or receiving data from some external system or a subsystem, there can be some errors, there can be some problems, there can be some behavior or performance issues. For example, you are doing file transfer, you are being told 10 millisecond will take for say 100 MB, but what you are witnessing is you are getting say time as 100 millisecond for the same data. There may be error. Initialization and termination error. How does a work start? How does a work end? How does a function starts and it ends? That means behavior. That kind of error can be generated by the black box testing. So the black box testing is generally applied after all the testing is over. So because this black box testing is not aware of control structure, its attention is totally on the information domain, the functional domain. So we have different kinds of black box testing and we'll be discussing few of them. So black box testing can be done using the boundary value analysis. It can be orthogonal array testing, equivalence partitioning, graph based testing, fuzz testing, and state transition testing, all pair testing. Boundary value analysis, orthogonal, equivalence, graph, these are we are going to take. Okay, I'm just saying black box testing are these. You may choose any of them or few of them depending upon your application. So black box testing are designed to answer how is the functional validity tested, how are system behavior and performance being tested, what classes of input will make a good test cases, is the system particularly sensitive to certain input values. For example, we can test for certain sensitivity testing. How are the boundaries of a data class isolated? We can use the boundary value analysis for this. What data rates and data volumes can the system tolerate? So stress testing, load testing, performance testing we can apply here. All these I'm talking about comes under system testing also. What effect will specific combination of data have a system on this system operation? Multiple combinations, some data can affect differently, some may affect differently. Because scanning, enumeration and penetration, these are the main thing for black box testing. We are not aware of, we don't want to go inside the system. Graph based testing. Graph is a pictorial view and it immensely help in understanding the problem, to analyze the problem and to solve the problem. So this testing is a kind of problem only. So better is, and how to generate these test cases, how to implement the test cases. So in black box testing, the testing begins by creating a graph of important objects and their relationship. In white box testing, we were doing the same thing. We used to find out the cyclomatic complexity, we used to find out the independent path and the basic path testing, and then it is applied. This is how the test cases are generated. Similar testing in black box also. In the white box also we created this graph. Here also we can create graph, but here we will have objects and we will try to show the relationship. So the test that will cover the graph so that each object and relationship is exercised at least once and the errors are uncovered. So what we do is we'll make a graph. Graph is a collection of nodes and these nodes will represent different objects. You can understand it as an object of an object oriented, or it can be separate object. You will understand now. The links that represent the relationship between objects, and all the nodes you see, we can describe the weight also. That can be a property. For example, a specific data value or a state behavior. For example, if A is 10, A plus plus we have done, it has become 11. So the state is different. And then the link weights. Node weight also we can give. The link weights also we can give. So the link weights that will describe some characteristic of a link. Nodes, they are represented by circles and these are connected by certain links. The link can be of different type. It can be directed link. Directed link that is represented by a single arrow. It indicates a relationship from one to another, only in one direction. We can have a bidirectional like this one also, a plain line. This is implying that the relationship applies in both the directions. It can be like this also, it can be simple line also. These are bidirectional links. Parallel links, these are used when number of different relationships are established between graph nodes. There can be multiple relationships between two nodes. So let me just revise it. These are the objects, these are nodes. There are links, how they are related. Object 1 is related to object 2. Object 1 and object 3 are related both ways. Object 2, object 3 are related in multiple ways. That is why we are having a parallel link. You can assign different weight values, the strength values. These are called the numbers. Okay, let us understand this with an example. Now let us say we have a word processing application like the Microsoft Word. How does the object can relate? The objects first will be whenever you invoke Microsoft Word, there will be a menu, file new. You will click file, new will come. So new file menu select is an object. The second object can be document window. Whenever we click on new file, there will be a window. Say plain clean window will come, and then we have a document text. This is the object 3. See, when you press new, a document window will come. Now you are going to write something in the document text. So this will be object 3. Now the first one, new file menu select. Now menu will generate a document window. So it can be only one directional. Document window will not generate the menu select. A menu you will not. You cannot go other way around. Okay, and the document window, whenever you are working on it, you will write certain things, because once you press a menu button, you will have a clean document window. You want some default setting, some white background. When you write, you want some font color like black. Okay, default color or preferences, the background color. These are the attributes. These are the weight being given to node number 2. And now we are giving link weight also. Link weight, so let us say it is 1 second. So this link indicate that whenever we press the new file button or menu, it should generate below 1 second the document window. And there is an undirected link between or say in a symmetric relationship between the new file and document text. and there are parallel links. This shows that they have relationship between document window and document text, because document window will contain document text. So we have parallel links. Okay. So this is just a simple example for you to understand how do we make the object and what are the relationship we can give and what are the numbers or weights we provide for graph based testing method of black box testing. But in reality, this kind of graph is more detailed. Okay, for a test case design, you need more detailed type of graph to be made. So there can be multiple type of graph. Bezier, he described number of behavioral testing method that can make use of certain type of graphs. Because it is not only about one or two testing. It is about behavior testing, performance testing. There can be different kind of nodes can be made. Okay, for example, transaction flow modeling. When you use the transaction flow modeling, then what will be the nodes and what are the relationship between the nodes, how the links will be found? Let us see. For example, a window, this document window you can check the say spelling, you can do multiple editing. There's so many things you can do on Microsoft Word. For that, we can have transaction flow modeling. Now here the nodes are going to represent the transaction, different transaction. So keep that thing in mind, and now I'll give you more examples. You are trying to reserve a ticket on airline reservation system. So what will be for example, the nodes will look like? The link represent the logical connection between steps, and the node will represent the step in some transaction. For example, a data object can be flight information input, and this is followed by an operation which is called validation available process. You can also use the finite state modeling. Again, we can make the graph. So the node will represent different user observable states of the software, because there will be different state. For example, A can be 10, A can be 11. So these are I'm talking about the user observable state. Each of the screen that appear, say some entry clerk takes a phone order or takes an order, this can be node. And what are the links? They can represent the transition that occur to move from one state to another. So what the link will show what is done so that the states are changed, and states are what? The observable behavior. For example, I'll just give you one more example for this finite state modeling. The order information is verified during the inventory availability lookup, and this is followed by customer billing information input. So these nodes are representing user observable states, and the link is representing the transition that occurred to move from state to state. This is the finite state modeling example. We can also use the data flow modeling. And data flow modeling, the nodes can be here data objects, and the links are the transformation that occur to translate one data object into another. For example, say some tax computation problem is there. So FTW, for example, FICA tax withheld. This is computed from the gross wages or the salary, GW. So what are the relationship? FTW is equal to some number into GW. Let us take, for example, the number is 0.62. Just a random number we are taking. So this is how the computation will be done. Okay. So this is how the data flow modeling you can make. In timing modeling, the nodes are or they can be program objects, and the links are the sequential connections between those objects. Again, in timing modeling, the nodes can be program objects. The links are sequential collection. So the link weights are used to specify the required execution times as the program execute. Let me tell you again, the link weights are number of execution time required as the program is executing. So these are different model you can use with reference to the graph. Equivalence partitioning. Though it is a test case design philosophy, before we go ahead, let us understand what is this equivalence. Any relation, that is, a set, is equivalence relation if it is reflexive, every element is related to itself. If it is symmetric, every relation A to B is also B to A. Transitive, if A is related to B, B is related to C, then A is related to C. So these kind of relations are called equivalence relation. That is, the values are equivalent. They are regarded as equivalent. Now, if we just divide them or take the subset of this equivalence relation, what do we get? We get the equivalence class. So equivalence class, subset of equivalence relation, and all the elements are equivalent. So equivalence partitioning is a black box testing method that divides the input domain of a program into classes of data from which the test cases can be derived. The important part is, an ideal test case single-handedly uncovers a class of errors. For example, incorrect processing of all character data, like that. So if you take any of these in this set, equivalence class, any value, for that you may not have to make many test cases. Only one element of the equivalent class can uncover all class of the error, or single-handedly. So it has come from equivalence classes, and I told you what is equivalence relation, what are equivalent classes, and if equivalence relation, reflexive, symmetric, transitive is there. Before we go ahead with the example, let me tell you the equivalence class will represent the valid or invalid states for the input conditions. Input conditions or value can be either a specific numeric value, it can be a range of values, it can be set of related values, that is a set, or it can be a Boolean condition. True, false, yes, no, right, wrong. So we have certain guidelines. So equivalence classes, how to make them? See, for every one, what we have to do, each of them. First one is, if the input condition, the condition is a range, then one valid and two invalid equivalence classes we need to define. If the input condition requires a specific numeric value or a specific value, one valid and two invalid equivalence classes are defined. If an input condition specifies a member of a set or related values, now here we will have one valid and one invalid equivalence classes. If the input is Boolean condition, one valid and one invalid classes will be defined. Okay. So how do we do this? Let us take an example here. And let us take the OTP example first. One-time password. So normally it is 6-digit, and we are also saying that it is 6-digit. So how do we equivalence partition it? We get this OTP in our mobile messages and emails. So this is a specific value, okay? But it is defined that it has to be 6-digit. So we can have valid values, that is 6 digits has to be there. These are the valid. And since it is a specific numeric value or set of related value, you can argue like that. But the main thing is, I've shown you the invalid, that is 4 digits or 7 digits. If it is not 6-digit, then it is invalid. 6-digit, it is valid. So either you can make one valid and two invalid, or one valid or one invalid. These are the classes. That is, we will take one value which is invalid, one value which is valid. 6-digit is valid. Anything other than 6-digit, that is the 7-digit or 4 digit, 3 digit, 8 digit. So you can make invalid class and valid class. Okay. Now coming to the other example, for example 6 to 10 is valid. So 0 to 5 can be invalid, and 11 to 14 is also invalid. This is how we take the equivalence partition in class. And the important part is we will combine the binary value analysis BVA with this, and that will create a more promising test case. So this is the equivalence partitioning test case design. How many valid and invalid test cases we have to make? Valid and invalid, both are test cases. Boundary value analysis. Now when you are traveling, you don't have map. Assume you don't have map. So if you're going straight, you don't have to ask anyone. But whenever you have multiple turns or a cross intersection, then you have to read the board. Here you have the problem. Similarly, most of the time, in the coding, the boundary values create problem. So boundary value analysis is one of the widely used test case design technique for black box testing. This is used to test boundary values because the input values near the boundary, they have higher chances, higher probability of error. So we'll make the partition, valid partition, etc. But error occurs more at the boundaries of the input domain rather than the center. So boundary value analysis leads to a selection of test cases that will exercise the bounding values or boundary values. So this boundary value analysis, it is complementing the equivalence partitioning. Once you have made the equivalence partition, say for example 2 invalid class and 1 valid class you have made, you see the examples also is given. And how do we do the boundary value analysis? In these 3 equivalence classes, we will take these boundary values and then apply the test cases. So boundary value analysis leads to selection of test cases at the edges of this class, equivalence class, if you apply equivalence class partitioning. So boundary value analysis, not only for the input domain, you can derive test cases for the output domain also. This is very important. For example, if you have divided this whole range into valid and invalid classes, for example, equivalence partitioning you have done, then the actual boundary value analysis will be done at 18 and 30. That is a value which is near 18 and near 30. So 28, 30, 31 and 17, 18, 20. These are the values which are of your concern while applying the boundary value analysis. These are the value I am making circle. Sometimes people say that the boundary value analysis, if we compare with the equivalence partitioning, though they are complementing each other, but BVA is considered more better because it may take the positive and negative values both, along with the minimum and maximum value. So what are the guidelines for BVA? How do you actually do it? So the guidelines or the way you are going to do it is, if an input condition specifies a range bounded by say values A and B, say A is 10, B is 100. So test cases should be designed with values A and B which are just above and below both A and B. For example, 10 you will take 9 and 11 also, 100 you will take 99 and 101 also. If an input condition specifies a number of values, if you have number of values, then what you will do? You will take the minimum and maximum numbers and then you will use the test case for minimum and maximum. And then the minimum, which is the value which is just above and below minimum and above and below the maximum. And this too also can be done to the output condition. For example, if you have a temperature versus pressure table. This is required as output for say certain engineering analysis program. Then how do we apply boundary value analysis to this output condition? The test cases should be designed to create an output report that produces the maximum and minimum allowable number of table entries. If you want a table, what will be the maximum allowable values? What are the minimum allowable values? This has to be done. This has to be your test cases. This is for the output condition. If the internal program data structure, they have prescribed boundaries. For example, if you are taking array, defining an array. Now if this array is 100, you have defined. So you know array starts with 0 and with 99. Most of the time the error comes at 100. If you want to access any number which is higher than the array being defined, there will be an error. So you have to check it at 98, 99, 100 and in between also some value. So a table has a defined limit of 100 entries, right? So be certain to design a test case to exercise the data boundary at the boundary. Now these are the valid and input say classification we have done, equivalence classes we have made. And then what you have to do is you have to take the values which are at the boundary of these classes. Negative, positive. That is how boundary value analysis works. Orthogonal array testing, OAT. Now what is an array? Simple array. It is two dimension. That is, you define an array like this. It is a contiguous settlement of memory elements. You can access any value here with some array with subscript. Okay. Now orthogonal array testing, when we have multiple dimensions, we need to have the orthogonal way of understanding. So orthogonal array testing is a software testing technique that uses orthogonal arrays to create test cases. This is all about minimizing the test cases. I'll tell you when the cases will be very high and how we can boil down to the low test cases. It is a statistical testing approach specially used when system to be tested has huge data inputs. So this orthogonal array testing helps to maximize the test coverage by pairing and combining the inputs and testing the system with comparatively less number of test cases for time saving. For example, 100 is there, you just need 10 of them. How is OAT represented? The formula is like this. So L, see, this is two dimension and I am talking about multiple dimension. For example, third dimension can be added like this. So you have to understand the orthogonality like this. Like the AX, Y, Z axis, then one more element, one more element like this. So we represent it by L, then runs, levels, and to the power we write factors. What are these? Runs, levels, factors. See, first of all, the runs, these are the number of rows in the array which translate into number of test cases that will be generated. Okay. Factors will be number of columns in the array which translate into maximum number of variables that can be handled. And levels will be maximum number of values that can be taken on any single factor. Okay, these are just definition, but we need to understand with an example. So let us take an example. This is an example web page. Just assume we have three distinct sections and these sections can be anytime hidden and can be shown. They may be visible, they may not be visible. So the first one, we say that this is the top part, top. The middle one is middle. The lower one is bottom. So a web page that has three distinct sections that can be individually shown or hidden from a user. Now let us see how do we make the formula and what all these represent? L, and whatever we write here, we'll write here, I'll tell you how do we get it. But first it is the power, that is, what is number of factors? Factors is 3. Top, middle, bottom. These are number of factors. Now the levels are hidden and shown. Every top can be hidden and shown, middle can be hidden and shown state, and the bottom can also be hidden and shown state. So the level is 2, factor is 3. 1, 2, 3 factors, and 2 is the level. And this 4 has come from where? This 4 has come from a table. Okay, this table I am showing you on the far right. So where was the factor? Where was the levels? It is 2 raised power 3, level raised power factor, and here was the 4 array type. So from 4, where has come? From where we deduce 4? See, most of the time people say 2 to the power 3 n equals 4. These are the combination. So for multidimensionality, if it is 2 raised 3, you will get 4, L4 matrix, this L4, the orthogonal. Then we have, if it would have been, say 2 raised power 4 or 3 raised power 4, n would be 9, so it would have been L9 3 raised power 4. Okay, I hope you got the idea. 2 is what, 3 is what? 3 is the number of variables, L is the variable states, or a variable can take how many states, and this 4 or 9 has come, that is from this table. Now how many test cases can be generated? 2 raised to the power 3. Sometimes people say, let us make it more easier, 2 into 3, 6 test cases. Most of the time it has to be 8, because this is the logical understanding. But even if we don't want to understand like that, 2 into 3 is 6. 6 test cases are there. Our main idea is to reduce the test cases. These are the simple test cases. Top can be hidden and shown, so test 1, test 2 correspond to it. Bottom can be hidden and shown, either hidden or shown, test 3, test 4. Middle can be either hidden or shown, it can be test 5, test 6. So 6 test cases are being designed. So how does this orthogonal array testing reduces the test cases? This is the conventional way of doing it. Orthogonal array testing will give you only 4 test cases. These are the test cases. And on the matrix, you can assume it to be a table. Top, middle, bottom, these are the 3 variables, variable 1, variable 2, variable 2. Every variable can take 2 values, hidden or visible, and these are the combination of the variable values for test 1. Let me just give you an example. Let me make it more easier. If we say the hidden is 0 and visible is 1. So the test case number 1 will be the top value will be hidden, the middle part will be hidden, and bottom value will be hidden. So if you make a orthogonal array, you can easily pinpoint 0, 0, 0, or the test case 2, hidden is 0, visible, 1, 1. Now this particular point can also be shown on an orthogonal array. So this 6 has changed to 4 just by using an orthogonal array. Okay, this is the use of orthogonal array testing. In this orthogonal array testing, as the number of input value grows, you can say number of variables, and each variable takes different discrete value. That is, each data item, different values can be taken. There are immensely number of test cases that can be made. For example, A can take 0, 1, 2, B can take say 0, 1, 2, C can take value as 0, 1, 2. Now, if ABC is okay, if you go up to Z, for the larger products or projects, it will be various variables, various input values. A can go up to 3, B can go up to 5. See, so exhaustive testing is not possible. Here we apply the orthogonal array testing, and this is applied when input domain is small but too large to accommodate the exhaustive testing. So OAT is useful in finding the region fault. That is, if A is 0, B is 1 and say C is 2, then the problem is coming. So this is the faulty logic. At this point, the logic is faulty. Let us take 3 input values, for example, 3 input items X, Y, Z. Now this X, Y, Z, so 3 values, and they may take, each of them can take 3 values. So how many possible test cases are there? 3 to the power 3, 27. Now this is manageable. Okay. What is the geometric view of the possible test cases? Here you have X, Y and Z represented with the X, Y, Z axis. And these round points are the possible test cases. If one item at a time, if we assume that the result is relatively limited coverage of the input domain, if we equally distribute it, one item at a time, if we distribute it using the L9 orthogonal array, or here you see, when OAT occurs, an L9 orthogonal array of test cases is created. So the L9 orthogonal array has a balancing property, and these test cases are represented by dark dot. In order to understand this, because this was just the theory, let us say we have a send function for some faxing application. 4 parameters are there: P1, P2, P3, P4. Or you can say 4 variables are there, and the function is send. So this is a function send. We have 4 variables: P1, P2, P3, P4. And each of these, that is P1, can take, say, certain values, 3 values. P1 can be 1. It can be 1, corresponding to send it now. P1 can be 2, send the fax 1 hour later. Or P1 can be 3, send it after midnight. So if one item at a time we take, that is just a simple way of representing it, P1, P2, P3, P4 combination. Now if you see all these combination, only one value is changed. Here it is 3, here it is 2. Only one value is changed because we are taking the policy of one input item at a time. And that will create immense pressure on the test cases. But these would only uncover only single mode faults. If any one of these has error, the faults can be computed. And what are the number of test cases required? 3 raised to the power 4. Okay, 3 raised to the power 4, which is 81. 4 variables are there, and each variable can take 3 options. 81. But when we go ahead with various numbers, we have a problem. So Fadke, he actually introduced it. Actually, this is called a Taguchi design. So Fadke assesses that we can have it solved by L9 orthogonal array testing. That is, if we have send P1, P2, P3, P4, a single mode fault is consistent problem with any level of any single parameter. If P equals 1 causes an error condition, it will be single mode failure. Okay. Now, the 1 and P1 and P2, we have to choose that also. That is called the double mode faults. If only P1 or P2 or P3, P4 is giving some error, it is single mode. P1, P2, double mode. Combination of all these is multi-mode faults. So what we do here is, we make a Taguchi design. And only 9 test cases we can make. Only 9 test cases. And this is a prescribed way of doing it. I am saying that this is 111, 222, 333 for P1. 123, 123, 123 for P3, P2. P3 is 123 and then becomes 231 and 312. P4 becomes 123, 312 and 231. This is you have to write. And now test case 1 will be P1, P2, P3, P4 for all these values. MBT or model based testing. First, let me tell you, this model based testing is a black box testing, and here it uses the requirement model for the test case generation. So you don't need to go into the detail of the structure part or the internal part of a software. The requirement model is the basis. So the MBT, it employs the UML state diagrams. Under these requirement modeling, we have made certain state diagrams, use case diagram, sequence diagram. So we will use the state diagram for making the model based testing or doing the model based testing, because this is the element of a behavioral model. So here, because the name is suggesting, we will create models. We will not do the actual thing. For example, if this is, say, a website and you are clicking somewhere, say add to cart, some other buttons should come up. So we have to model it, that when we click that other button, what will happen to the previous button. So these are the models, that is in the web page, for example, which page we are going, in which page, which section a user can go, where he can navigate. Maybe he can go from 1 to say 3, 1 to 2 different pages he can go, which section he is going to go. So this needs to be modeled, and that can be done using the behavioral model, which is the state diagrams. So model based testing requires 5 major steps, because this involves creating also. That is, we will analyze an existing behavioral model. If this behavioral model is there, it is okay. Otherwise, you need to create a behavioral model in order to do the model based testing. Because behavioral model is what? It shows, it indicates how your software is going to respond or act when an external event or a stimuli or a stimulus is there. That is, some software is given. Basically, we are trying to talk about the event driven. Some events and some stimulus. We have already discussed how to create these behavioral model. But let me give you a brief hint. Evaluate all the use cases just to understand the sequence of interaction within the system. First, use case is the basis. Then the interaction you have to understand, and identifying the events that drive the interaction sequence, and understand how these events relate to specific objects. That is, how the interaction is going on, which event is producing what. Then we have to create a sequence for each of these use cases. Use cases, that is the requirement. So now you have to build a UML, that is a unified modeling language state diagram for the whole system, understanding the point 1, 2, 3. And this state diagram, once you have made, you have to review the behavioral model for accuracy and consistency also. This behavioral model will be the basis of model based testing. The second step is what? Because already we have made behavioral model. So this already we have made, and as I said, the state diagram is the basis. So this state diagram, we have to traverse this behavioral model, and then we have to specify the inputs that will change the software from state to state or transit it from state to state. Then we have to review the behavioral model, and then we have to see what are the expected result. For example, the state is changing, A is 1, A becomes 2. So we have to note the expected outputs. For each set of inputs, that is the test cases which are specified in the step 2, we have to specify the expected outputs as in the behavioral model. Then we have to do it, means actually execute the test cases. This can be done manually, or we can use the test script, and we can use the testings too. Main thing is we have to see the expected result and the actual result. If there is some non-correspondence, corrective action is required. So MBT is uncovering the errors of behavior, software behavior. So as I said, MBT is extremely useful where the event-driven application is the main context. In any software development life cycle or software processes, there are various work product being produced. Normally, we relate the testing with coding. But we were doing the black box testing, white box testing. We learned so many aspects of these two testing. Okay. But there are certain more work product like the documentation, requirement specification, the software design, the user manual, the compilation guide. So these are all also deliverables. Now this is the duty of the software team to also test the documentation, all the documentation along with the user manual, help facilities, installation guide, compilation guide. There are so many different work product or the documentation generated as a result of all these software processes. Okay. So user manual, user guide or customer guide, as I said, they are different product, different results of documentation will be there. So what happens if you are as a user using a user guide or a manual or say an online help and it is not helping you? It is just there and not being properly made. It will be so frustrating for you as a user. So for every software test plan, documentation testing is a must. We just don't think about documentation testing, but it is integral part. The documentation testing normally happens in two phases. The first is the technical review. That is, a person will sit, he will see the editorial clarity, semicolon is not there, the sentences are not properly formed, or they are ambiguous, or they are not pointing to what we were wanting. For any novice user, it should help. And the live test, that means using the documentation in conjunction, in help with the actual program. For example, you created an installation guide or you created a user manual. Now we will start with the installation guide and we'll try to install the software. Or with the user manual, we will try to do certain activity or achieve certain functionality. Okay, but if you are using it and if you are stuck somewhere and this user manual is not helping, that means the testing is the main criteria to find out these are the errors. For this, that you have to do testing. So live test for documentation, this may use certain techniques which are very similar to black box testing. For example, if the usage of the program, use of certain functionality has to be tested, graph-based testing method can be used. For input, classes of input and their interaction, we can use the equivalence partitioning or the boundary value analysis technique. This can be a help. Okay. So graph-based testing, equivalence partitioning and boundary value analysis, depending upon what exactly documentation part you are going to see. MBT, you can use model-based testing to ensure document behavior and what is the actual behavior of the software. Does it coincide or there is non-correspondence? So please understand, testing documentation is as important as testing your code. Testing for a real-time systems. First, you have to understand what are real-time systems. Real-time systems are all those systems where the time is critical. Something has to happen in the prescribed time limit. The time constraint is rigid. If something has to happen in 1 millisecond, it has to happen in 1 millisecond. Okay? For example, in flight system, in those systems where the life is involved, okay, for train system like say defense armaments. So here you see, if you microwave you're using 30 seconds you input and after 30 seconds what happens? Microwave stops itself. And in this 30 seconds, you have pressed some button, but sometimes you can press another button, you can open the lid or open the door. These are interrupts. So most important thing in real-time system are interrupt. Interrupt are those which want attention. So it can be preemptive, it can be non-preemptive. Sometimes the interrupts are so important, like trap, they have to be accepted. Sometimes the real-time systems may say postpone attending the interrupt. For example, CPU. There are certain times the CPU will work and will wait for acknowledging the interrupt. Otherwise, some interrupt it has to acknowledge by stopping its work. So there are real-time systems, soft, hard real-time systems. So there are two partitions, hard and soft. Soft real-time systems like all the operating system which are RTOS, that is, they want certain time limit, this has to happen. But if it doesn't happen, there is not much of a concern. Hard real-time system, it is much of a concern. It can be catastrophic. So the time-dependent asynchronous nature of real-time application adds a new element to the testing, which is time. Asynchronous because anything can come at any time. Time is important. So the test case designer, he will use all the conventional test cases, but he has to understand and consider the event handling, as I am saying, like the interrupt processing, timing of the data, and the tasks are going, say, parallel. So parallelism of the tasks or the processes have to be dealt with. So test data for the real-time system in one state may result in proper processing. For example, test data at state 1. But the same test data for different state of this real-time system may lead to an error. This has to be checked and verified. Let me tell you that again, why it is difficult to test the real-time system. Time constraints are there, conventional methods cannot be used directly, and you can get some unpredictable outcomes. For instance, just take the example of this photocopier machine. Now this has a hardware and a software combined. So we can call it as a real-time system. So there are certain control keys. The real-time software that controls a new photocopier, it can accept operator inputs. That is, a user or a machine operator can hit a reset or darken with no error when the machine is making copies, everything is going good. But the same operator interrupts, same pressing of the button when the machine is not copying state, but it is somewhat jammed. The paper is inside, it is jammed. Now it can give you some other result, or it can give you some diagnostic code. Where is the jam? What is the location of the jam, cause of the jam? That is the error. Okay. So copying state, things can go fine. But what about the jam state? So there can be some code like error 003. I'm taking just an example. So software test must consider the impact of these hardware faults on the software processing, because now real-time system is a combination of a hardware and a software. So it's a combined combination. So if some hardware failure is there, you have to consider that also. So there are certain strategies. We are going to discuss a 4-step strategy for real-time software testing. First is the task testing. There are different tasks. Test for each task has to be done independently. You can always do the conventional task testing because you will see the logic, errors in the logic and the function. But the timing and behavior cannot be found here. You cannot uncover errors in timing and behavior. For that, you have to go for behavioral testing. And you can use certain, models which can be created by automated tools, or even you want to create it, you can create it. You can simulate the behavior of the real-time system. And then you can determine and examine its behavior as a consequence of some stimulus or external events. First thing in behavioral testing is you can use these state diagrams, or you can, automated tools are there, you can create your own model. So like the equivalence partitioning, these events which can be interrupts, it can be some control signals, you can also categorize them for testing into equivalence classes, and then you can use one of them and test it. So how to do this in behavioral testing? For instance, in a photocopier only, the events for the photocopier, the user might have the interrupts like the reset counter, or there can be some mechanical interrupts from inside coming, like the paper is being jammed, or some system interrupt, oh the toner is low, the ink is low, this can come, and some roller is overheated, so this is some failure modes. So all these events, each of these events, these needs to be tested individually, and that can be done using the behavioral testing. Okay. What is the third one? Inter-task testing. See, once there is an error in individual tasks and system behavior, these are errors you have isolated, you have found and say done something for them. Now our testing will shift to the time related errors, because this is a real time system. So there can be tasks which can communicate at any time. These are asynchronous tasks. When they are communicating or talking to one another, you have to test them with different parameters. For example, the data rates, the processing load for this inter-task, whether there is some synchronization errors in these tasks. Let me tell you, we have already done for the two-step individual task, we have checked, system behavior we have checked. I am talking about the inter-task testing, that is different data rates you can change, the processing load, and there can be other parameters also, and that can give you this synchronization error. Now let me give you an idea. If the communication is happening using a message queue or a data store is there, that is from task 2, first thing goes to message queue, then goes to the task 1, or a data store is in between, then you can change the size of this data store, message queue, you can change or shorten or make the size more, then you see what errors are coming. The fourth is the system testing. The software and hardware are integrated, and then the system tests are conducted, because we need to know the interfacing errors. What are the interface errors? Since the real-time systems, they are processing the interrupts, so testing the handling of these Boolean events, 0, 1, yes, no, you have to do it or not, is quite essential, because in the system testing is an integral part. So as I am saying, the state diagram, using these which have already been made in the requirement modeling, tester would develop all the possible interrupts and what is the processing. So tests are designed to assess. There are certain system characteristics when you are doing system characteristics, like are the interrupt priorities properly assigned, and are these interrupt properly handled with proper priorities? Is processing of each interrupt handled correctly? And then, because these two are important, then we have to see the performance also. Does the performance of processing time of each interrupt handling procedure conform to the requirements? Is it happening in time or it is exceeding it? Does a high volume of interrupts, because multiple interrupts can come, does a high volume of interrupts arriving at very critical times, that may create a system to dysfunction or the performance issue is there? Okay, this is all about this discussion today. Thank you so much.